Okay, so here's the review for test number 1 that we are getting late delay on. So feel free to fast forward to the places you need. Feel free to stop it if you need. I'm just going to go fairly quickly through the review sheet. So first thing is, for the entire part of section 1, where we're finding the equation of the tangent line to the curve at a point, you want to remember the steps are: find the derivative, because that'll be your rule for slope. Step 2, plug in your x value. And then step 3 is you use point slope form to write the equation of your line. So that's what the steps we're going to follow here, starting with A. So our derivative in this case is, we're thinking of this as x to the 4/3 instead of the cube root of x to the 4th. So we're going to get 4/3 x to the 1/3 plus 2x minus 1. Step 2, we're going to plug in the number 1 and have 4/3 plus 2 minus 1, which I inadvertently put on the answer sheet as 3 1/3 when it's really 2 1/3. So I'll hopefully have gone back to fix that before you see it. But then I'm doing y minus the y value equals that slope times x minus your x value. So for B, same idea, different equation. We need to think of this function as x squared minus 3 to the -3rd power, because we only know how to take the derivative right now of a function to a power. So our derivative is going to be -3 x squared minus 3 to the -4, because the -3 comes down. We change it by dropping it down 1 degree, and then we're going to multiply on the derivative of this inner function, which is 2x. So my derivative is -3 x squared minus 3 to the -4 times 2x. I'm going to plug in the x value, which is 2. And I'll have -3, 4 minus 3 to the -4 times 2 times 2. So I plugged in 2 here to make that 4, 2 here will make that 4. And this will all multiply to -3 times 1 times 4, which is -12. Equation of my line, y minus my y value equals m times x minus my x value. And then for C, my function is just going to require the simple power rule. So my derivative will be 4/3 times 3/4, which is 1, x to the 1/3 when I subtract 1, 3/4 times 4/3, which is 1, x to the -1/4. I'm going to plug in the number 1 for my x's to figure out my slope, which is going to turn out to be 2. And then I am going to write the equation of my line, y minus my y value equals m times x minus my x value. And that's how you write the equation of a tangent line, if you have the function and you have the point. A little bit different on number 2, because number 2, I want to figure out where the graph has a certain slope. So same first step. I need to figure out the derivative. And in this case, I'm thinking about this function as a function to the 1/2 power. So my derivative is 1/2 x squared plus 2 to the -1/2 times 2x. General power rule. But rather than plugging in a value for x right now, I'm trying to figure out what value of x I could plug in so the slope would be 0. So I'm solving this equation. In order to solve that, I can see that my 1/2 and my 2 are going to divide each other out. And this is when it's a really good idea to put negative exponents in the denominator, because the only way to make a fraction equal to 0 is to make the numerator equal to 0. Doesn't matter what's in the denominator as long as it's not 0. So 0 over 0 wouldn't be 0, but 0 over any other number is. So in this case, if x is 0, I'll have 0 over the square root of 2, which is in fact 0. So the place where it has that slope, you could answer is when x is 0. You want to be a little more specific. Plug your 0 into your function and make it a point when x is 0 and y is the square root of 2. So doing the same thing for b, my derivative would be 6x minus 4. And I want to know when that equals -9. I'm just going to solve that little linear equation and say when x is -5/6. And I could be more specific and plug that back in and also have the y value. But this is an x value for which the derivative is -9. Number 3 is all about writing and simplifying the difference quotient. So the difference quotient I just jotted down over here. It's going to look a little different for each situation. For A, I'm going to keep my h in the denominator, subtract the function, and 2x plus 2h minus 5 will be the function evaluated at x plus h. And that is simplified. There's nothing not simple about it. The only thing I want you to remember, though, is that we did rewrite things like this using the conjugate. And you may have to do that on the test if you are taking a limit. So don't forget that multiplying by the conjugate, although it doesn't simplify in this case, it might be a necessary step for the test. And you'll know you'll need to do that if you're taking a limit as h goes to 0, because you would try to plug in 0 for h and you get 0 over 0. So we did have problems like that. You want to feel comfortable being able to multiply by the conjugate. And remember, when you do that, you do not multiply out the denominator. You just would leave the denominator as it is. But you would multiply out the numerator, and that would have the effect of getting rid of your radicals. So you'd have the square root of 2x plus 2h minus 5 minus 2x plus 5. And then you would have opposites that you could get rid of, and h's you could divide out. And so just as a quick reminder, if it was a limit problem, you wouldn't want to stop right there. You'd need to know how to use the conjugate. For B, sorry, my dog is ringing the bell because he wants attention. If you hear that in the background. So we have, in this case, 1 over 2x minus 6 is our function. So over here, we would be plugging in x plus h, so we'd have 1 over 2x plus 2h minus 6. That's not simplified. So to simplify it, we're going to get a common denominator, which is these two multiplied together. And then our numerator is going to become this numerator times that denominator minus this numerator times that denominator. And that's still all over h, because that was in the denominator. We're going to collapse our denominators together. And while we're at it, we will have some things in the numerator that could subtract each other away, like 2x and negative 6. So we'd only have the negative 2h left when we distribute. And then finally, we can divide out our h's as long as they're connected by multiplication. So these two, and that's my simplification. And then last but not least, we have functions that you are expanding out. And that would look like putting your function here. No, not 3x squared. X squared minus 3x. And then in front, if I left enough room, we'd have x plus h squared minus 3 times x plus h. So in order to simplify that, we would have to FOIL, distribute, and end up with x squared plus 2xh plus h squared minus 3x minus 3h minus x squared plus 3x all over h. And remember that the way we know we did this right is everything in the numerator that doesn't have an h as a part of its term should have an opposite that's going to subtract away. And once that's subtracted away, you can take the h from each of the terms that's left, factor it out, so you can divide it out. And that will be simplified. So that's how we handle difference quotients. Limits. We had a couple, I alluded to what you would do with a limit if you had a square root. These are all limits without square roots. The first step with limits, if you're approaching a number like you are in A and B, is to try to plug in the number that you're approaching. So for A, that would look like I'm doing the limit as x approaches -2. Well, let's just let x be -2 and see what happens. So in the numerator, I get 0, and in the denominator, I get 0. So that's a big failure. That doesn't get me anywhere because 0 over 0 is not a definable number. It doesn't give me an answer. It does tell me there is a limit, but it doesn't tell me what it is. So then we go back to the drawing board and we try to factor to see if we can get the x plus 2 factor to divide out. And in this case, we can factor the numerator, like x plus 3 times x plus 2, and divide it out. So as long as x isn't the value -2, which it's not, I'm just trying to get close to -2, my limit is 1. For B, when I try to plug -2 in, that's my first strategy, I get 4 plus 10 plus 6 all over 0. That is the limit does not exist. If you have a number that isn't 0 over 0, that means your limit does not exist. So finally, we're doing a limit to infinity. So infinity is an idea. I can't plug infinity in and square it and multiply it by 5. That's not the strategy you want to use with infinity. Infinity strategy is factor out the highest degree in the numerator and the denominator. So then we were left with 1 plus 5 over x plus 6 over x squared, because we're dividing x squared out of every term, and 7 plus 2 over x squared. The reason that we do that is to show that the x squareds could divide each other out. And then if I go to try to let x get close to infinity, every one of these terms that has an x in the denominator is going to become closer and closer to 0. And I'll be left with the 1 and the 7 as 1/7. And we talked about how this had to do with finding horizontal asymptotes. It's the same way you did in Math 22. When you had matching values here, when you were looking for a horizontal asymptote, you took the ratio of these two coefficients. And that's giving us the same result. There's a picture next where I'm supposed to decide what x values this graph is differentiable or non-differentiable at, where it's not continuous. And so there's a connection between these two. If we can find places where it's not differentiable, we'll know that those places are also If we can find places where it's not continuous, we'll know those are the same places it's not differentiable. So anything that's in B has to be in A. So let's start with continuous. It's not continuous when I have to pick up my pencil. So if I start drawing this graph, the first time I have to actually pick up my pencil is right here when x is 2. So the only place on this graph where it's discontinuous is when x is 2. So that means that it's also not differentiable there. If it's not continuous, it's not differentiable. But there's one other place where it's not differentiable, and that's right here at -1, because it is not differentiable when your graph takes a sharp turn like that. So everywhere else we're fine, but no derivative when it's not continuous and no derivative when it takes a sharp turn. The limit as you approach 2, remember we talked about that being you on one side, your friend on the other side. You're walking forward, she's walking back. Are you going to end up at the same height when you get closer and closer to this value of 2 on the x-axis? And no, you're not, because you're going to end up higher than she is. You're at different levels in terms of the vertical level. So there is no limit as you approach the number 2. When you approach the number -1 on the x-axis, if you were walking up the line and she was backing up the curve, you would end up at the same point in space. There is a limit. And that limit is the y value that you would be at, the height that you would be at that time. And that height is 1. Number 6, fill in the rest of the piecewise function to make it continuous. So we talked about the fact that if you have a rational function where you've got a common factor top and bottom that are going to divide out, that creates a hole in your graph. Once you divide it out, you just end up with this linear equation, x plus 3. That is the equation you want to use to fill in the hole. So when x is the value 3, if you use the function x plus 3, then this graph will be continuous. Because before, it looked sort of like this. It was a line, and then when we got to 3, we had to put a hole because we weren't allowed to plug 3 into this function. And then it continued on. So what I've just done with this is I filled in the hole, made it continuous. I also could have just filled it in with the number 6, because if it's x plus 3 only when x is 3, then it's always 6. So either is a correct answer. Number 7, we've got some notation you want to remember. The notation for 7 is take the derivative, plug in 4. So for A, you would want to think about the function like this. It's 5, not over 5x minus 2, whoops, but times 5x minus 2 to the -1. So I'm using the function on the bottom, and instead of having it on the bottom, I'm giving it a -1 exponent, which is exactly the same thing. So if that's my function, this is my coefficient, this is my exponent. I take the derivative by multiplying -1 times 5, not changing the function that's inside. The inner function doesn't change, but I drop the degree or the exponent down 1. And then I don't forget to multiply on the derivative of that inner function. That's the general power rule. So what this is going to look like is -5 times 5. I could say -25. And that's all over 5x minus 2 squared. I'm going to put that back in the denominator. Because I'm supposed to plug the number 4 in now for x. So -25 over 20 minus 2 squared. Put the 4 in there, so 20 minus 2 squared. So it's -25 over 18 squared, which is 324. For b, this is the second derivative. So I need to take the derivative and then I need to do it one more time. So the function is 3 times 4x to the 1/2 power. 4x is living under a square root. So my first derivative, I've got a 3 and a 1/2. I'm going to multiply and get 3/2, not change the function inside, drop the exponent down 1, and then multiply on the derivative of the inner function. So 3/2 and 4, I can multiply them together to be the number 6. And then I'm going to do it again. This was the first derivative. I'm supposed to get the second derivative. So here's my coefficient and my exponent. I'm going to multiply. I'm going to drop the degree down to -3/2. And then I'm going to do the chain rule, multiply by the derivative of 4x. So my final answer is -12, -3 times 4. And then I've got 4x on the bottom to the 3/2 power. I'm supposed to plug the number 4 into that. So I've got -12 over 16 to the 3/2 power. And 16 to the 3/2 power is the square root of 16, which is 4, cubed, which is 64. And then you can reduce that down, divide by 4 again, and you can get -3/16. Moving over to the back, we've got the idea of a cost function for a company, and we want to know the actual change in cost to raise the production level from 20 to 21 units. So the actual change in cost would be plugging in 21 units to the cost function, plugging in 20 units and subtracting them. That's how we'd find the change. So I'm going to use my calculator and I'm going to put 0.1 x cubed minus 6x squared plus 136x plus 200. And I'm going to go to my table set, start it at 20, go up by 1, and I can get the two values I want. So 1,336.1 and 1,320. And I want to subtract those, and that will be the actual change in the cost if I decide to make 21 units instead of 20. To estimate the cost to make 21 units, I would have to take, that's A, that's B. I would have to know two things. The first is the cost of 20 units, and then I want to add on the marginal cost of 20 units. So marginal analysis says if you have a place to start and then you add on how the function is moving at that time, you can end up with the next value of your function. So I know C of 20. I'm going to pretend for a minute I don't know this, because this is, I mean, I actually do know that, but I'm pretending with marginal analysis that that would take me into the future and I don't know it. So I'll need the derivative of my cost function, which looks like this. I've got 0.3 x squared minus 12x plus 136, and I'm going to plug 20 into that. So 0.3 times 400 minus 12 times 20 plus 136 is 0.3 times 400 minus 12 times 20 plus 136. That's 16. So C prime of 20 being 16 is saying that if I decide to make one more unit, it's going to cost me $16 more. And that means that if I add the 16 onto what I've already paid, my estimate of what it's going to cost to make 21 units is $1,336. Actually, it was 10 cents more. So my estimate is pretty close. So my marginal cost of 20 units is pretty close to what I get when I actually subtract the cost of 21 and 20. But marginal means, a marginal cost means the cost for one more. And it's actually the approximate cost for one more. And that would help answer this. C of 20 is the cost to make 20 units. C prime of 20 is the cost to make the 21st unit. And that's approximate cost of the 21st unit. Average rate of change over an interval. So the average rate of change over the interval is where we started last time, last class. And we were talking about average velocity, and we said that the way we find it is we do a slope of a secant line. So it looks like plugging 3 into your function, plugging -1 into your function, subtracting, and then 3 minus -1. So f of this, if I call this A and B, f of B minus f of A over B minus A. So I got my calculator here. I'm going to put, since I need 2 function values, I'm going to put my equation in here. And then I'm just going to go to my table, second table, and I'll start my table at 3 and go by ones so that I can grab the numbers I need. So f of 3 is -13. So f of 3 is -13. F of -1 is 3. And then 3 minus -1 is 4. So -16 over 4 or -4 is my average rate of change for those 2 functions, or for that function between those 2 points. Okay, and then for the second one, I've got different functions, same average cost. I want to go 8 minus 2 in the denominator, and then I'm going to plug 8 into my function, so 1 over the square root of 2 times 8 minus 1 over the square root of 2 times 2. So that is 1/4 minus 1/2 over 4, which is -1/4 over 4, which is -1/16. And there is my average rate of change for this function. Instantaneous rate of change. So that's a different question. If we go back to the original A, this was average. Instantaneous means take the derivative and plug in where you want to know the instantaneous rate of change. So say said the initial value, so that would be -1. So I want the derivative with -1 plugged in. The derivative here is -6 times x, so that's -6 times -1, plus the derivative of 2x is 2, and the derivative of 8 is 0. So I'm ending up with my instantaneous rate of change being 8. 6 plus 2. So that's very different than the average rate of change over the interval. Here, I want the instantaneous rate of change, so I need my derivative. And this function, I want to think about it as 2x to the negative 1/2. So my derivative is negative 1/2, 2x to the negative 3/2 times 2. The negative 1/2 came down, it changed to negative 3/2, and then I multiplied on the derivative of the inner. So that ends up being negative 1 over 2x to the 3/2. And when I plug in the starting value of the interval, which is 2, negative 1 over 4 to the 3/2 becomes negative 1/8. So my instantaneous rate of change was negative 1/8, while my average rate of change was negative 1/16. Except I subtracted wrong, sorry. I was thinking something looked wrong there, sorry. 8 minus 2 is 6, I was dividing. So then this is negative 1/24. Sorry about that confusion. So there's my average rate of change and my instantaneous rate of change. So just as a recap on that, when you see average rate of change, you want to take the function values subtracted over the x values subtracted. That's how you do a slope. For instantaneous rate of change, you want the derivative, and then you're going to plug in whatever number you want the change at, because the instantaneous rate of change is the slope of the tangent, and the average rate of change is the slope of the secant. This is looking at your rate of change as you're driving to your friend's house, how long it took you in the denominator, how far you went in the numerator. This is like the radar gun. And then finally, number 10, this is marginal analysis. If I don't have the function, up here for this number 8, I had the function, and I could do marginal analysis with the function, but now I'm not going to have the function. I'm just going to have a value. Sorry, things are falling apart here. So my values are going to be what I'm going to use with the marginal analysis instead of actually taking a derivative. So that's going to look like thinking about a starting place with these values, and that starting place is an x value of 36. I know what's happening in my function when I plug 36 in. I'm getting 200. So that's a place I know, a way to start. I know 36 matches with 200. I also know that this is the slope of the tangent line there, and that has a -4 slope. So if I decide that I'm going to take a step out to the right, my y value is going to drop 4 units. If I take an entire step out, so 1 step to the right means 4 steps down. And marginal analysis is on the line. I'm using the tangent line to make my decisions about values. So if I want to know what f of 37 is, that is 1 step to the right. So f of 37 will be f of 36 plus f prime of 36 times how many steps I went. This is f of 36, this is f prime of 36, and this was the thing we called h, how many steps to the right I wanted to go. So that's going to leave me at 196. F of 35 means that I want to take 1 step to the left. And that looks like this. I'm starting at 200 on my height. I know that the derivative is -4, but if I'm trying to back up and go to the left, h is -1. And that means my answer is going to be 204, which makes sense because it should be higher than 200 if I'm going to the left. F of 36.5. Now I'm going to the right, but I'm only going a half a step. So I want to take 200 plus negative 4 times 1/2. Only a half a step, and that's going to leave me at 198. And then finally, F of 35.25, that's going to the left, but it's going 3/4 of a step to the left. Because 35.25, if you imagine going from 35 to 36, 35.25 is right here, and that's 3/4 of the way back. So that's going to be 200 minus 3, or 197. So that is the way we do our marginal analysis for when you're given only points and not the entire equation. So that is my quick review, and hopefully you'll take a look at the topics as well. And if you see any topics on the sheet that you have any questions about, feel free to contact me.